Good afternoon, students. In the last lecture, we have seen about elements. If we see the architecture of the embedded system, in that we have seen different elements of the embedded system. Which are these? Input port, we have some sensors. At the output port, we have actuators. Then we have system core, that is chip. Which kind of controller we are using for that controlling of the embedded system. Now here in system core, depending upon the application, whatever we are going to be used, according to that we can choose the controller. Now here for that controller, if we consider the microcontroller for the some specific reason or for as per our purpose, we have to choose the microcontroller. So what is the architecture of that particular processor or the controller? Here there are two architectures we can combine, or you can say the compare. First is Harvard architecture and von Neumann's architecture. Now how it will work? Now if you see the diagrams, both in this, what is the difference? By just take a look on it. What is the major difference between these two? Can anybody understand? We have, if you see for Harvard architecture, we have separate memory, and here we have common memory. Now there are two types of the memories if we consider the architecture. One is a program memory and data memory. So what is the use of the program memory? We can save the code. It is also called as code memory. We can save the instructions, that is what the coding part into the program memory. And data memory is what? Where we can save the operands. You might be seen about, or we know the meaning of opcode and operand. Opcode is what? Operational codes. So that controller can understand the language and it will decode it, right? And second part is operand. Operand is nothing but what? Operand is the controller can do the operations on it. It may be a different operations, and that specially performs into the ALU. That is what it may be, arithmetic or logical. Now here if we see, this is a single sharing bus and memory is a common. So it means that the route or the path through which the data bus is same for program as well as data. Program is what? Actual code, and data is what? Operands, right? So in this case, that is what in von Neumann architecture, if you read it, these controllers shares a single common bus for fetching of both instruction and data. The program instruction and data stored in a common main memory. That is what both the, you can say, the opcodes and operands in a similar memory. But here the program or the opcodes are in a program memory, and then data memory is what? That is what operands are here. So normally execution of any instruction, we need the three different processes, or you can say the three cycles, not cycles we can say. These are the three stages. That is what execution of instruction in a three different stage. That is what first is fetching, second is decoding, and third is execution part. We will see. So as here in Harvard architecture, this will have separate bus for the instruction bus, and that allows data transfer program fetching to occur simultaneously on both sides. It means that this is your processor of the controller. It will fetches that code from this side and data from this side. That is what parallel operation is going on. But if you see the von Neumann's architecture, it doesn't happen because the bus is what? Single or shared. So either you can fetch the code or you can code, or otherwise what? Second part is what? Data or the operand. That means what? At a time either you can fetch the code or data, but here in this case no. Here is a fetching from the, that is what, codes from the program memory and data from the data memory. So simultaneous operations are going on. So which is a faster in performance? Which architecture, Harvard or von Neumann's? Harvard, because the parallel operations are going on. Is that clear? Okay. Now this is about Harvard and von Neumann's architecture. If we the comparison sheet or a table in which Harvard we have separate buses for instruction and data fetching. Instruction means what? Opcodes, and data means what? Operands. Here von Neumann architecture there is a single shared bus for instruction and data fetching. That is what common lane is there or bus is there. Easier to pipeline, so high performance can be achieved. What is the reason behind that? Why Harvard architecture is high performance based, or you can say that can be achieved because the pipelining. What is the pipelining? The opcodes from one side and operands from another side on this, because the buses are different. But this could not be happen in a von Neumann's architecture because this is a shared single bus, right? That is why the reason is that Harvard is comparatively high cost. This will be the cheaper. One more thing, in Harvard architecture, no memory alignments. What is the reason? What do you mean by memory alignment first? We have a memory structure, we have a space, so we need to be what we have to do? We need to be, you can say there are different shelves, you can say, in a cupboard. So it means that we have to arrange that. That is what segregation or separation will be there. So here there is no need of alignment because both memories are separate. We cannot differentiate as a opcode or data. But here, in this case, von Neumann's architecture, sorry, here in this case, this is separate or single. This will be single memory. So that is what this allows self modifying the codes. That's why we require the, you can say, the memory alignment. Since the data memory and program memory stored physically in different location, no chances of accidental, you can say, the corruption of the program memory. Here both are separate. There is no collision between the data. Data in true sense, that is what is operand, and another is opcode. So there is no collision of the data because buses are different, or you can say the roads are different. So there is no collision of the data, there is no corruption. But if von Neumann architecture, it is a shared bus, so there may be a collision of the data and accidents may happen. That means what? There is a data corruption, you can say. Accident means what? Data corruption. Okay, this is about Harvard and von Neumann's architecture. Now we'll go for load and store operation. What is that? I will give an analogous example of the load and store in that. If we analogous example of the load and store, there is two meanings of this load and store. There are two parts. Whenever we go for coding point of view in a microcontroller, we can save the data into two parts. One is the memory, another are the registers. So how we can understand this? I will take an analogous example. We have a fridge, we have kitchen platform. In a fridge, and the ingredients is called as a data. So either, that is what we want something, ingredients from the fridge, we open it and just moving from, that is what the data means what? Ingredients which are already into the fridge that we can keep onto the kitchen platform, right? So there is a moving of data from fridge to the kitchen platform, that is called as load, right? Now here fridge is a memory and kitchen platform is what? Registers. Got it? So we can move that data. This is the first operation, that is nothing but load. And is storing, after completion of our work, we can keep the things into the fridge. It means that this is a storing operation. Is that clear? What is a load and store? Okay. This is about load and store. So here we can see the memory access relate operations are performed by the special registers instructions, load and store. If the operand is a specified memory location, operand means what? If we take the comparison with analogous example, whatever I given, that is what fridge and the kitchen platform. So here memory location is what? Fridge, and ingredients is what? Data. The content of it loaded to the register, that is what? We are moving the data from fridge to the kitchen platform. And the load instruction stores the data from specified register, that is what? After finishing of my work, calculations, whatever the processing, I just kept back to the into the fridge. That means what? Memory location. Is that clear? What is a load operation? So it means that in a load operation, there is a movement from memory to register, and in store operation, store में क्या होगा? What will happen? We are moving from register to memory. Is that clear? So this is a simple operation of load and store. Okay, we'll move ahead about instruction pipelining. Now just now we have seen about architectures, Harvard architecture and von Neumann's architecture. Which one is the faster one if we compare this? Harvard, why? What is the reason? Separate memory. So how the performance is higher in that case? The reason is that instruction pipeline. Now in instruction pipelining, what will happen? This is a clock cycle. There are 3 different pages. Already I told you there are 3 different stages. First is fetch. I can write here fetch, decode and execution. FDE, fetching, then decode and then execution. What does it mean? Fetching means what? We can fetch the data. Decode means not to understand the operation, and execution to process that operation. Now here, this is a clock cycle. I can write here, this is F, this is D, and third one is E. So in that case, I have to execute multiple instructions, but in a normal sequence, the process will be like this. First is I1 is the instruction, then I2, then I3, and so forth, and so on, right? So first instruction will come, that instruction to be executed and passes through the three different phases. What is fetch, decode and execution. Now here, if I compare, this is the first, second, this is the first part, then this is second one. These are the actually machine cycles, but sake of convenience, I take one cycle as a fetching, decode and execution, how will happen. So I can write here, this is I1, and I return, this is the first machine cycle, this is second, this is third, this is fourth, fifth and so on, right? So the fetching of I1, then what is the next process to execute of I1? Fetch first, then second, decode and then execution. So it will be move here and then it will move here. So how many cycles you can say the clock cycles? 3, right? So for execution of I1 we need 3 cycles, right? Now this is a normal phenomena of the execution of the instructions. As this I1 comes, then in second cycle I2 will be there, right? It means that there is a parallel operation is going on. How? Fetching of this is I2, fetching of I2 and decoding of I1. Got it? Then third cycle, this will be I3. Now here this I2 will be here, right? Then this will be, this is I2, because I2 fetching, decoding of I2 and execution of the I2. Same thing happens with I3. This is a fetching, but if you remember or you can understand from this, for the first cycle only, if we consider there is no instruction into the queue before execution, that's what this part is not empty, because this is a past instruction actually, but we starting from here, that's why we consider this one. So in the second cycle there are 2 operations are going on. One is fetching of I2 and decoding of I1. For the third one, fetching of decoding of I2 and execution of I1, right? So it means that if you consider for I1, I take 3 clock cycles, right? Okay, what about I2? I2 is starting here, but this part is common. So this one is I2 up to this, and then this one is I3, right? So it means that how many cycles? This is 3, 4 and 5. And how many instructions we are able to execute? 3. But, but if we go for normal or conventional method, that will take how many? 9. Now here what is how many cycles we are taking? Only 5. That is called as the instruction pipelining. Are you getting? That is what parallelly operations are going on. That is what F, D and E. Next type of system core is application specific integrated circuit. Application specific is what? Already we seen for embedded system there are different purposes are there. What are the purposes? There are so many purposes are there. If the specific purpose is there, we have to go for ASIC. A microchip designed to perform a specific or unique application, it is used as a replacement to the conventional general purpose logic chips. Then ASIC integrates several functions into a single chip and thereby reduces the system development cost. So it integrates, ASIC will integrate the several functions, because suppose I want to make a product. For that I want to add some features in it. Adding up features, what I need? I need a different, you can say the blocks or ICs. So whenever I integrate, for example, I want to make a, you can say design, or you can say the design of smartphone, and I want to add some features. But every feature has a separate IC or integrated circuit. So I have to integrate all these together and it will form a, what it will form? It will form application specific integrated circuit. That means what? Multiple ICs, that is what I can build in, and then I will add the features. Okay, most of the ASICs are proprietary products. As single chip, ASIC consumes very small area in a total system and thereby helps in design of smaller system with a high capabilities or functionalities. Now what will happen? Suppose I have a main system core in which multiple surrounded ICs are there, right? So its system become bulky. But whenever I am adding this, or the size of that particular system will be compact, because I am just adding the features, adding the ICs. But suppose I have separate circuitry for each, the system may be bulky. So to avoid that, we can use ASIC. ASIC can be prefabricated for a special application, or it can be custom fabricated by using components from reusable building block library of components for the particular customer application. Suppose I made some circuit. For example, this is a display, that's what LED moving display. That display size is different. This is not exactly whatever we available in the market. So I need a casing. For that casing, I have to make a specific provision. I go to that fabricator, I give my dimensions, and I said you have to prepare the box of that dimension. That means my circuit will fit into it, or my LED panels will be fit into it. So that is what here ASIC can be prefabricated for the special application, and it is custom fabricated by the using components from the reusable. That is what it is already used, or you can say the new one, the building block or some library components. Then fabrication of ASIC requires a non-refundable initial investment. That is what this is about, the costing and all, for the process technology and configuration expenses. Whatever the expenses will be there, that has to be bear. If non-recurring NRE is borne by the third party, that is what these are the some commercial applications. But majority case, if we see for the system core, we have programmable logic devices, that is called as a PLDs. Now, what is PLDs? Programmable logic devices. It is a device which has a logic, and by using that, that's what program can be used to, you can say, change the logic, and accordingly we can control that particular element. The logic devices provide specific functions, device to device interfacing, data communication, signal processing, data display, timing and control operations, and almost every other function a system must perform. Matlab, what are the applications? It may include device to device interfacing. Can you tell me what is a device to device interfacing? In microprocessor, we don't have a ports, inbuilt ports, so we need PPIs. Suppose I want to control some element, or you can say I want to control, that's what relay drivers are there. Instead of 8255, some ICs are there. Or a simple example is that I want to glow some LEDs. I want to control these LEDs, LED panel or LEDs. But 8085 microprocessor, we don't have inbuilt port. So how to communicate with that? Through using PPI, right? So that is under the heading of device to device interfacing. Then data communication, whenever we want to communicate with any other device, that can be possible with PLD. The important aspect of the PLDs are, there are into two categories. First is fixed and programmable. Now what does it mean? The circuit in a fixed logic device are permanent. There is no any change. They perform one function or set of functions once manufactured, and they cannot be changed. That is what this is one-time programming, you can say. The manufacturer will do, this is a fixed program, and there is no chance at all we cannot, we cannot make changes into that. That is what this is a flow, and it has to be happen. And what about programmable? Let's see. Programmable logic devices, PLD offer customers a wide range of wide range of logic capacity features, speed, voltage character, and these devices can be configured to perform any number of functions at any time. It means that there is a chance to the user, he can modify that, you can say the contents, or you can say the reprogrammed, what we can say in simple language. Designers can use inexpensive software tools, quickly develop, simulate and test their results by using PLDs. Suppose you design one circuit, I said prepare a PCB, design is ready, you have to prepare a printed circuit board and just go for the, you can say the check the output. Is it possible? No. So what we want something that can be like a simulator. That means what? You just build that circuit on a breadboard, test your results. If it is okay, then we go ahead with the next step. So same thing is here. There's some software inexpensive, these are not expensive tools. Software tools are quickly develop, simulate and test their results by using PLD based design. Is that clear? So it means that PLD is used to develop, simulate and test the result. PLDs are based on rewritable memory technology. Rewritable memory technology means what? That can be the device is reprogrammed to change the design. Suppose I did some program and I tried to, you can say by using some tools, I tested this particular my device, but whatever the results, whatever I am getting, it is not up to the mark. Some changes are there. So I can make the changes in that and I can get the better results. But if you go for the fixed one, no, we can't, because this is already permanent or fixed.